In this video, we're going to look at how to integrate some problems where, upon first look, use substitution may fail. And so we need to look at some different algebra techniques we may have in order to integrate some of these problems until you learn some other methods. The first one we're going to look at is a type of problem where some long division will be used in order to integrate. And so we're going to look here at this very first problem. So I want to find the antiderivative of x squared minus 1 divided by x squared plus 1. Now the reason why use substitution fails is because if I let u be either the numerator or the denominator, and I go through the process and let u equal, let's say, x squared plus 1. The derivative of x squared plus 1 would be x to the 1 power, so I'd still have an x squared up here, which lies an issue, which is why use substitution fails. So what we're going to do is we're going to do long division, and we're going to rewrite the problem. So long division is I would take my denominator, x squared plus 1. Now we're going to account for all powers of x. And then we're going to divide that into the numerator, which is x squared plus 0x minus 1. And we do that, so we'd end up, let's see, 1 would have to be multiply the x squared by, I multiply it out, so we'd have x squared, 0x plus 1, long division we subtract, and we wind up with a remainder of negative 2. So what we can do is we can rewrite our original problem as the indefinite integral of 1 minus 2 over x squared plus 1 dx. And so I'm going to write in that form, and we're going to look here to integrate that problem. So what we can do is we can split that integral up. So we can split that integral to be the indefinite integral of just dx minus the integral. Now what I'm going to do here for the second one is I'm going to take that 2 and I'm going to pull it out here. And so we'd have 2 times the indefinite integral of 1 over x squared plus 1 dx. And now so I have 2 separate problems to integrate. So start with the one here on the left. The antiderivative of dx would just make x. And we have minus 2 times, now find the antiderivative of 1 over x squared plus 1. Well, this is the derivative of inverse tangent. So the antiderivative would be inverse tangent of x. And because we have indefinite integration, we need to have plus c for that constant of integration. So there's our antiderivative. All right, next we're going to look at the technique where we would need to expand in order to integrate. And so expansion, this technique is often effective when the inside function does not have the derivative present on the outside. So let's look here at an example where we would use this. So finding the antiderivative or the indefinite integral of sine of x plus cosine of x, and this is being squared. Now I have to improve this. This should have dx on the end. And so if I were to let u be the inner function, sine x plus cosine x, its derivative would have to be outside of here, and there's nothing outside of here other than dx. So what we would do in this case is we would fully expand the problem. And so I multiply the problem out, and we would have sine squared x plus 2 times sine x cosine x plus cosine squared x dx. Now from here I would continue to rewrite and say, well, wait a minute. All right, the sine squared plus cosine squared x just makes 1. So I really have 1 plus, and now we have 2 sine x cosine x. Well, I could make my problem even simpler here to work with, because 2 sine x cosine x is the double angle form of just sine of 2x. And we have dx on the end. So we'll break this up, and we would integrate this as 2 separate problems. So we'd have the indefinite integral of just dx plus the indefinite integral of sine of 2x dx. And so we're looking here at these 2 separate problems. The antiderivative of dx is just x, and then now we're looking at the sine of 2x, which I could do substitution. I could let u equal 2x, which means du is equal to 2 dx. So 1/2 du is equal to dx. And so we'd have x plus the indefinite integral of sine of u times 1/2 du, well, I could take that 1/2 and put it outside of the integral. And so we would continue on and say, okay, well, the antiderivative of sine of u is negative cosine of u, so I'd have negative 1/2 times cosine of u, but instead of u, I'm going to substitute the 2x back inside. And then we have plus our constant of integration plus c, and there's our antiderivative. All right, so the next technique we're going to look at would be when we would have to complete the square. Now, the technique of completing the square is useful when you have an x squared term and an x term in the denominator, and you have a constant in the numerator. And so we look here at an example where we would go through the process of having to complete the square. And so I have 2 over x squared minus 6x plus 10. And so the process of completing the square, basically what I'm trying to do is I'm trying to rewrite this denominator here, where I'm showing some binomial being squared. And so if I'm looking at that denominator as x squared minus 6x plus 10, if I was going through the process of completing the square, I would work with these two pieces here. And I would say, all right, well, we would generate some binomial that would be x minus, you half the number right here in front of the x to the 1 power, so it'd be x minus 3 being squared. And now we still have this plus 10. Now the issue is we've now created an expression that is not equivalent to the line before, where if I was to multiply out that binomial, you would have x squared minus 6x plus 9. And then we'd have plus 10. So you see what the value is that we had that we did not originally have up here. So what I would need to do is I would need to subtract here by 9, so that way I still would maintain my balance in my equation, where it would take me back to what I originally had. So our denominator would be x minus 3 squared plus 1. All right, so we rewrite our problem, where we rewrite our denominator as x minus 3 being squared plus 1. Now, it might not initially look like something that we can take the antiderivative of, but I'm going to take that 2, and I'm going to pull that 2 outside of the integral. And what we have is we have 1 over x minus 3 being squared plus 1 times dx. Now, we're going to use u substitution here. I'm going to let u be x minus 3. So if I let u equal x minus 3, du is equal to simply just dx. So we'll do a change of variables, rewrite our integral, and our integral becomes 2 times the indefinite integral of 1 over u squared plus 1 times du. Well, 1 over u squared plus 1, that is in the form as the derivative of inverse tangent. So we have 2 times inverse tangent of u plus c, and then we're going to resubstitute in for u. And so our answer for this antiderivative would be 2 times inverse tangent of x minus 3 plus c. Okay, the next technique we're going to look at is when it is often helpful to separate the numerator. The technique to separate the numerator is useful when there's more than one term in the numerator after u substitution fails. And so here we'll look at an example. And so we have the square root of 1 minus x squared in the denominator. In the numerator of this indefinite integral, we have 3x plus 2. And so the reason why u substitution fails here is if I let u be 1 minus x squared, and I took the derivative of that, I would have just 2x. And the problem is I could do something here, but that plus 2 kind of gets in my way. So what we're going to do is we're going to split this up before we start going through the process of trying to integrate individual pieces. So I can break this up as each term in the numerator will get its share of the denominator. So I'd break it up as 3x over 1 minus x squared square rooted. And then I need to have parentheses because I'm making 2 terms. So plus 2 over the square root of 1 minus x squared, and then dx. Now these problems become, I look at them in terms of individual pieces. So I want to find the indefinite integral of 3x over the square root of 1 minus x squared dx. And then I want to find the antiderivative of 2 over the square root of 1 minus x squared dx. And then we'll just combine our answers at the end. It could be helpful for us to take these constants, the 3 and the 2, and take them outside of the integral, and we'll rewrite. So we basically have 3 times the indefinite integral of x over the square root of 1 minus x squared dx. And then we have plus 2 times the indefinite integral of 1 over the square root of 1 minus x squared dx. All right, so what we're going to do is I'm going to come up here because I'm kind of running out of room, and we're going to work. So from here, we're going to integrate each little piece. I'm going to treat this kind of like 2 separate problems where I'm going to work and I'm going to combine my answers here at the end. Well, looking here at this one, I'm going to have to do u substitution here. So we're going to let u equal 1 minus x squared. So the derivative of u, written in differential form, would be negative 2x dx. Well, we have the x dx part, but we just don't have the negative 2. So I'm going to divide the negative 2. So we have negative 1/2 times du is equal to x dx. And then we're ready to do our change of variables. So we'd have 3 times the indefinite integral of 1 over the square root of u times negative 1/2 du, which would make negative 1 over 6 times the indefinite integral of u to the negative 1/2 power du. And so we would continue on. We would do the power rule for integration. We get negative 1/6. We would increase the exponent by 1, so that'd be u to the positive 1/2 divided by 1/2, so I'd multiply by 2. And then now that we have a form of an antiderivative, we would take and we would plug in. So we'd end up with negative 1/3 times the square root of what u was square root of 1 minus x squared for that first piece that we want to combine with our second piece. So we'll come back up and we'll look at this right-hand side that we want to find the antiderivative of. And if I'm looking at this, the 1 over the square root of 1 minus x squared, that looks like the derivative of inverse sine. So we would have 2 times inverse sine of x for this piece. And now we have to put these pieces together. And so our final answer for antiderivative will be negative 1/3 times the square root of 1 minus x squared times 2 times inverse sine of x plus c. And so there's our antiderivative. All right, another algebraic technique that could be used if u substitution initially fails is to do partial fraction decomposition, which is basically I'm going to break up my problem. I'm going to separate my problem into the addition of 2 separate rational functions. This technique is going to be useful for if I have an x squared term and an x term in the denominator, and I can factor my denominator. The previous one, when we did the completing the square, we could not factor that denominator, and so we used the process of completing the square to see if we could make it work. And so this time, what you're going to have is you're going to have a factorable denominator that I am going to need to split up, because if I'm trying u substitution, I would let u be my denominator here. I'd have the du would be 2x plus 2, and I have negative x plus 7 dx, and that would get a little difficult to work with. So decomposition, what you would do is you're going to take your initial problem, and you're going to factor that denominator. So x squared plus 2x minus 3 factors to x plus 3 times x minus 1. And so I'm trying to break this up into the sum of 2 fractions, a over x plus 3 plus some number b over x minus 1. And so if I'm going through the process of breaking these fractions up, basically what I would do is I'd work this right-hand side and I would get common denominators. and I would rewrite what I had. So if I went through the process of getting common denominators, I'd have negative x minus 7 over x plus 3 times x minus 1 is going to equal my a fraction. To have that same common denominator of x plus 3 times x minus 1 would have to get multiplied by x minus 1. My b fraction, to have the common denominator of x plus 3 times x minus 1, would have to get multiplied by x plus 3 on top and the bottom. And so now that I'm in this stage, what I would do is I would work here with my numerators. And so we're going to say negative x minus 7 is equal to a times x minus 1 plus b times x plus 3. Now we're going to use a method called the cover-up method here. We're going to strategically pick x values that will eliminate one of these constants and allow us to solve for the other one. So what I would do is I'm going to let x equal 1. Because if I let x is equal to 1, it's going to cancel out the a term and let me solve for b. So I'm going to put in 1 for all my x's. So I'd have negative 1 minus 7 is equal to a times 0 plus b times 4. And now I would go solve. So negative 8 is equal to 4b. So negative 2 is equal to b. So we solve for b. Now we're going to solve for a. Well, we're going to pick the other zero. So we're going to let x equal negative 3 because that will zero out the b part. And we're going to put negative 3 in. So we would have basically 3 minus 7 is equal to a times negative 4 and then plus b times 0. Well, we would have negative 4 is equal to negative 4a. So a is equal to 1. So what we've done is we've decomposed our initial problem that should be the addition of two separate fractions. So I'm going to put 1 in for a, I'm going to put negative 2 in for b, and we're going to rewrite our problem. And so we put 1 in for the a, and we put negative 2 in for the b, and we rewrite, and so our problem becomes this right here in purple. And so now it's broken up into one big rational function, been broken up into two smaller ones so we can actually integrate both of these. And so what I'm going to do is I'm going to break this up into two separate integrals. So we have the indefinite integral of 1 over x plus 3 dx minus, and I'm going to pull that constant of 2 outside of the second integral, so minus 2 times the indefinite integral of 1 over x minus 1 dx. And now we're going to integrate. Well, in both of these problems, we could do substitution. So I could let u be equal to x plus 3 here in this first one. So if u was x plus 3, du would equal dx. And so really you're looking at the antiderivative of 1 over u du, which is going to be the natural log of the absolute value of u. And so if I put that back in, we would have the ln of the absolute value of x plus 3 to be this left side. And then we're going to have minus 2 times whatever we get for our second integral, where I could do u substitution here for the second one. So if I let u equal the x minus 1, du could equal just dx. And then, so basically you'd have 2 times the indefinite integral of 1 over u du, which is going to give us 2 times the natural log of the absolute value of u here. And then we substitute back in what we had u representing for the second one. So it'd be 2 times the natural log of the absolute value of x minus 1. And then don't forget the plus c on the end.